Oftentimes in chemistry, it's better to understand something conceptually rather than just memorize it. Because when you understand something, when you truly understand the why behind it, that allows you to apply it better. It allows you to see the bigger picture. So today, we're going to try learning VSEPR through understanding electrostatic repulsion, okay? So I've represented that here with your blue arrow, and it is absolutely central to understanding VSEPR without needing to write down a table, right? So I wrote down some things about VSEPR here. So one thing that's important is that these electron pairs obviously are going to repel each other. They're both negative charges, so going to repel, right? That makes sense. Now, they're going to arrange themselves because of that to minimize repulsion. Because they repel each other, they're going to try to minimize that torsional strain, okay? They're trying to reach that lowest energy state, and that's through minimizing repulsion. Now, finally, the last thing that's important to note is that these lone pairs, rather than single bonds, are going to take up more space. Now, the reason why that is because these non-bonding electron domains, these lone pairs, are a valence orbital, and they're pulled on by only one nucleus, okay? But, in contrast, this single bond, it's formed from the constructive overlap of atomic orbitals and is attracted by two nuclei. So because the non-bonding is only attracted by one nucleus, it's going to be taking up more space than that single bond, okay? So, on this slide, I have the steric number in the corner, okay? Steric number. It's a very big N. So, your binary linear molecule might also be called linear, right? There's only one bond here. There's one connection, one object around this, so that's why it's steric number 1. Here, there's two, right? There's two of these bonds, two of these objects around the central molecule. So that's why it's steric number 2, okay? So now this makes sense, right? When there's one connection, it has to be 180 degrees. This bond isn't really going to be bending or anything. Same thing with this one, right? There's the furthest away these guys can get from each other is 180, right? If you had them any closer, the repulsion would increase because the repulsion is going to increase with lesser distance, right? So getting them as far away as possible is the way that that repulsion is minimized, and thus the lowest energy configuration is found. Now moving on, we have steric number 3 over here. So 3 trig, a null planar, right? Tri is 3, steric number 3, right? So this base molecular geometry or electron geometry, sorry, kind of makes sense with the steric number. So 3 bonds, right? If you imagine a circle, it's a really bad circle, but if you put 3 of these guys here, the furthest way they can get from each other is 120, right? If you divide 360 degrees by 3, 120, right? So now comes the first time we were adding a lone pair, okay? So adding this lone pair, let's say this atom, we're going to substitute a lone pair, okay? Now remember, the lone pair is going to increase repulsion, so therefore this bond angle is going to shrink, okay? It's going to be less than 120, because compared to a single bond, the non-bonding electron domain, the lone pair, has greater repulsion. Now, one thing I do want to mention is that angular can also be called bent, okay? B-E-T, okay, bent. Now, if you go to the 4th slide, I'm going to skip ahead a little. Bent can also be called angular, okay? So these are really interchangeable. It depends on who you ask. Now, I personally prefer to use angular and bent separately. Angular for 3, bent for 4, because that to me helps like give you a more specific answer. If I tell you something is angular versus something is bent, you'll know the steric number. Okay, so now steric number 4. Okay, so there's 4 objects surrounding this central atom. tetra is your root for 4, so 4 steric number, tetrahedral, right? Now you're no longer planar here. This is a tetrahedron, so if you imagine these are the vertices, these would connect to form your 3-dimensional tetrahedron, okay? So now, let's go through that same process, okay? You're adding a lone pair. Let's make this. You're substituting that lone pair in there. So that's pyramidal, right? So now, instead of being 109.5, it's less than 109.5 because this lone pair is going to have more repulsion than this single bond over here, okay? So now, right, pyramid, right? This has 3 bonds, kind of like a pyramid, a triangle, right? You can kind of see, if you look at the molecular geometry, you can kind of see a pyramid type shape, right? And like in the back here would be your base here, right? And that's why it's pyramidal, right? Now add another lone pair, and this repulsion increases yet, right? Even more repulsion, right? So bent or angular, right? So this is even more, less than 109.5. And your kind of rule of thumb here is each lone pair you add is going to be roughly about, let's say, 2.5 degrees lesser. So bent is usually around like maybe 104.5, give or take. Now, let's move on. Steric number 5 over here, okay? So the way you remember this, trig by, trigonal bipyramidal. 3 and 2 is 5, right? So the other thing you have to think about this is say, okay, another way you can remember this is like, okay, there's 2 pyramids here, right? You got pyramid 1 on top, right? Pyramid 1 on top and pyramid 2 on bottom, right? So bipyramidal, 2 pyramids, okay? So that's why it's bipyramidal. And trigonal, the trigonal part, is from the fact that it's a triangular base, okay? This forms a triangle right here. So now, let's ask, why is this 90 and why is this 120, right? Because memorize these bond angles, but also understand them. Understand the 3-dimensional relation as to why they are, right? And that will make your life easier when you're trying to figure out the rest of these bond angles. So you have the equatorial bonds, and the equatorial bonds are kind of like in this same plane as A, okay? They are the B right here, and the axial bonds, they are the up and down ones, okay? So now, when you have axial to equatorial, this bond angle right here, this bond angle is going to be 90. And that makes sense, right? This is the furthest away they can get, right, with the trigonal base. And now, when you look at this bond angle, though, the equatorial bond angle, that is 120, right? And it kind of reminds you, going back to trigonal planar, right, 120, because the base is trigonal, right? So now that's why it's 90, that's why it's 120. Now let's say I add a lone pair. An important thing for this one specifically is that your lone pairs are going to be added equatorially, right? They're going to be added equatorially. Now the reason why that is because when you add it equatorially, you only have 1, 2 other repulsions to worry about. When you add it axially, 1, 2, 3, axial is more crowded, so it's going to go to the less crowded one, equatorial, okay? So now let's add it equatorially, seesaw, right? So now it's going to be less than 90, less than 120, because this lone pair is going to have a greater repulsive force than the single bond. And the way you remember seesaw, right, is you can think of, that is the shape, right? It's a seesaw, right? It's now the angle might be a bit less than that, but that's the general idea. And you can imagine like 2 kids on here, right? And that's why it's named seesaw, right? It seems kind of random if you're just memorizing a table, oh, it's seesaw. But when you understand the shape and the electron geometry and the the electrostatic interactions, then it makes more sense, right? Now, once again, we're going to add another lone pair equatorially, right? So now that's going to create even more repulsive force. And right, notice that there's only one equatorial bond left, and this angle right here, it's going to be close to 90. Okay, so now I wrote less than 90 because remember, these lone pairs still have a repulsive effect. So it isn't 90 exactly. It's going to be slightly less than 90. Okay, it's going to be pretty close to 90, but not exactly, right? And finally, linear, right? Now all of your lone pairs are equatorial, right? And now your axials are the only ones that are left, right? So now you might expect that, oh, these lone pairs are going to distort it. It's not going to be linear, but it is linear. It's going to be 180 degrees because linear 180, right? Why that is because these, remember, are in that trigonal fashion, right? So these repulsions are all going to cancel each other out. So it's going to form a net linear molecule, okay? So remember, 5 try by 3 plus 2 is 5, and then you just add lone pairs, increase repulsion until you get linear, in which it goes back to 180 because those non-bonding domains are going to cancel each other's repulsive effects out, leaving only your axial bonds, okay? So now 6, right? We're pretty close to being done. 6. Now 6 is kind of confusing, right? Previously, your prefix right here, linear, trigonal, tetrahedral, trigonal, bipyramidal, lines up with the steric number, but here it doesn't. Octa is 8, 6 is your steric number. And the reason that is because this is an octahedron, 1, 2, 3, 4, 5, 6, 7, 8 sides, despite having 6 vertices, right? So you just have to remember the octahedral, is referring to the fact that it's an octahedron rather than the fact that it's 8 bonds, because it's not 8, it's 6. So you have to just think it's an octahedron, so 6 vertices, steric number is 6, okay? So now note that this is 90, right? It's not multiple because all of these are going to be 90 degrees apart from each other, right? Symmetric, adding a lone pair. Now, because it's symmetric, right, you can really add a lone pair wherever. I find it easiest to visualize. If you add a lone pair on the bottom, it's a square-based pyramidal. It's a square pyramidal, and right, I said based because like the name is square pyramidal, but it's the base of it. The square is a base of this pyramid, right? And this lone pair, you're adding it so it becomes a pyramid, but its repulsive effects, right? Make sure that this isn't like a flat guy, right? It's going to be slightly less than 90 because of that repulsive effect. But then now it's important where you add it, okay? You have to add it, the next lone pair, across, directly across from the first lone pair, because you're trying to minimize that repulsion, right? And that makes it 90. And it's the same reason as for this linear molecule right here, right? These lone pairs are opposite from each other, so their repulsive effects are going to cancel out, right? So these are going to be left as just 90 degrees, right? And square planar, right? So pyramidal, right, because you're adding this so it becomes a pyramid shape, right? And planar because it's a square and it's planar, right? It kind of makes sense. And these lone pairs are going to cancel, so that's why there's no net repulsion on them. So now 7, right? Now this goes back to our trend of the steric number following your prefixes, right? Pentagonal, bipyramidal, 5 and 2, okay? So this is similar also to your trigonal bipyramidal, right? All you're doing is you're just adding more equatorial bonds, okay? So you still have 2 axial bonds, right? You still got this and this, your 2 axials. Now you have 5 equatorial bonds. So if you imagine a circle again, and like, forgive me for how poorly it's drawn, but if you imagine 5 of these bonds here, right? The most minimal repulsion is going to be 360 divided by 5, which is 72, right? That's why it's 72 here, because these equatorial bonds, the 5 equatorial bonds, are trying to minimize their repulsion. And 90 here, obviously, is the same as trigonal planar, right? trigonal bipyramidal, where you have your 90-degree bond angle between your axial and your equatorial, right? Versus here, you have your 72 degrees interaction between your equatorial and your equatorial, right? So that's why it's 90 and 72 and pentagonal bipyramidal, right? 5 and 2 is 7. You're just adding 5 equatorial bonds. Now, let's do some practice, okay? Let's put it into place. So, H2O, right? I'll give you a minute to draw out the Lewis structure. You can pause the video, and then I will show the answer. Now, SO2, do the same thing, pause the video, and then I will show the answer. Xenon difluoride, pause the video, and then I will show the answer. Iodine pentafluoride, pause the video, and then I will show the answer. Now, assuming you got the Lewis structures correct, now you have to think of, okay, there's 4 electron domains, so it's tetrahedral, but you have 2 lone pairs, so it's now bent, right? Now, same thing here, right? You have 3 electron domains, but one of them is a lone pair, so that repulsive effect increases and makes it angular, right? Now, you think here, right? You have 5 electron domains, but 3 of them are lone pairs. 3 of them are non-bonding. So, it's going to be a trigonal bipyramidal electron geometry, but your lone pairs are going to cancel, so it's going to make it linear, molecular, and like molecularly. And then iodine pentafluoride, that's going to be this shape, right? Assuming you got that correct. And think there's 6, so octahedral electron geometry. But now I have 1 lone pair, so that's going to be square pyramidal. Okay. Thank you for watching. I hope you enjoyed that. I hope it was informative. And yeah, I hope you have a better understanding of electrostatic interactions now and how that's going to create these molecular geometries.